Okay, hello everyone. This is Mohammed and my colleagues Mohammed Ayman and Cesar Farhan, who has wrote the report. Today we will talk about improved baseline with visual instruction tuning paper and discuss LLMs and LLaVA. Next. Here's the agenda that we were talking about today. The first one I'll talk about overview and demo, and my colleague Mohammed Ayman will continue with what's new and compression with Soda. Okay, next. Okay, let's start with LLMs. LMMs. Here's an example of how multimodality can be used in healthcare. LMMs that can accept multiple inputs such as text and images. And here in this example, and this picture shows a multimodal multitask AI model, which is a type of machine learning algorithm that can process and analyze data from multiple different modalities such as images, text, and audios. The example in this image shows a multimodal multitask AI model being used to diagnose a patient rash. This model is trained on a dataset of medical images and text in this example. The model is also being used to answer the user's questions about what caused the rash and other questions about the, uh, the diagnosis itself. Also, the model can do this by combining its knowledge of the image with its knowledge of the text data. Next. Okay, next. Here where I will talk about what LMMs achieved. LMMs is typically are a type of artificial intelligence that can process and understand multiple modalities of data, such as text, images, and audios. This makes them much more versatile and traditional AI models. The first thing, LMMs have made significant progress in understanding and responding to visual instruction. So LMMs are still under development, but they have the potential of revolution a wide range of industries, from healthcare to education to entertainment and other industry. And another thing, LMMs can combine information from multiple modalities to get a more complete and accurate understanding of situation. For example, an LMM that can process both text and images could be used to diagnose a medical condition more accurately than a traditional AI model that can only process text. The last thing, LMMs can automate tasks that would otherwise require human intervention. For example, an LMM can be used to automatically generate subtitles for videos or translate text from one language to another. Next. Here I will talk about the LMM's architecture. There's a common architecture that have of LMMs. The first common architecture is pre-trained visual backbone for encoding visual feature. The function of this architecture is serve as a foundation for encoding visual features from input image. It is typically a neural network that has been pre-trained on a large data set to learn general visual representation. And its role is extract high-level features from the images, capturing patterns and structure that are relevant for understanding visual content. And the second common architecture is pre-trained LMM for understanding user instruction and generating responses. The main function of this architecture is this part of architecture is responsible for understanding user instruction presented in natural language and generating appropriate response. And its role is contributes to the model ability to comprehend and respond to textual instruction. And the last common architecture is vision language cross-modal connector to align visual encoder output with language model. We will talk more about cross-modal and MLB in the next slides. But in the main concept, the MLB cross-modal connector is a simple and efficient way to combine text and images. It has been shown to improve the performance of LLaVA 1.5 on variety of benchmarks. And LLaVA 1.5 is a simple LLM architecture, and we'll talk about it in the next slide. Next. Okay, LLaVA 1.5. LLaVA 1.5 is a newer version of original LLaVA. It represents a novel end-to-end trained large multimodal model that combines vision encoder and Vacona for general purpose visual and language understanding, and is setting a new state-of-art accuracy on science QA. LLaVA 1.5 achieving impressive chat capability mimicking spirals of the multimodal GPT-4. And it is a powerful and data-efficient LLM that can be trained on a relatively small dataset. And also, it's a promising approach to build a general purpose for visual assistants. LLaVA 1.5 has achieved the state-of-art, as I said, SOTA on 11 different benchmarks. This has been made possible through modification made to the original LLaVA, which is the first version of LLaVA. Next. Next. Okay, here's where I will show you a sample demo for LLaVA, where we provide the model with a photo, and we ask the model about what's unusual about this image. And the model was respond accurately, actually, and its respond that there is not a typical scene as a man ironing clothes on a top of car and something like that. Next. Here's where you can find the full live mod demo from the website of LLaVA. Next. Okay, here where I leave the mic to my colleague Mohammed Ayman to continue the slides. Thank you all.
Okay, thank you, Mohammed. Now we're going to talk about what's new in this version of LLaVA, all the modifications made to the original architecture and the training to get the new results. So first, the MLP connector. So a strategy to align vision encoders and large language models that were separately trained is to use an MLP vision language connector. In the original paper, they used a simple linear projection matrix. In the new architecture, they used MLP, and more specifically, a two-layer MLP to better connect the vision encoders output. In this case, it's CLIP with 336 pixels with the embedding space of the language model, in this case, Vicuna. Another thing they used to enhance the performance is the addition of academic task-oriented visual question answering data sets. They were inspired by done on this by Blip paper. And as you can see here, these are examples from the Open Knowledge VQA dataset. It contains pairs of images and questions about various domains. These require visual understanding and visual reasoning. And usually the answer is a single word or a very short sentence. Other than VQA datasets, they use also optical character recognition datasets and also region-level VQA datasets. And these help the model better understand and process and localize fine-grained details in the images. One problem of using these VQA datasets, this is a problem that they faced in the struct blip discussed in this paper, is the model being overfitting the VQA dataset. So basically, since the answers are very short, the model overfits to the and when you try to make a conversation with the model, it ends with very short answers. And to combat this, the authors of LLaVA used a technique in which they appended response formatting prompts, like for example, for the OKVQA dataset, they appended answer the question using a word or phrase. They also scaled many parameters, like the image resolution. For the original paper, they used 224 by 224, and for the new architecture, they 336. They also used GQA and ChatGPT datasets, and these help the model acquire better linguistic and visual understanding capabilities. Also scaled the model parameters. So the original paper only uses Vicuna 7 billion, but the new paper also uses both the 7 billion and 13 billion variants of the model, and they noticed improvement with the model. So now let's compare this work to the other state-of-the-art models on both benchmarks and also data. So here, as you can see in this figure, the LLaVA 1.5 model outperforms the other state-of-the-art models on all but one of 12 benchmarks. And as you can see here in this graph, they achieved that with very, very little training data compared to the others, because as you can see here in the graph, they had to use the scale for the x-axis. That's how big of a difference it is. The LLaVA 1.5 model uses orders of magnitude less data samples for training, for both pre-training and instruction tuning, compared to two other competing models like QuenVL, InstructBlip. So our conclusion is that this model is very impressive, and makes it even more impressive is its simple architecture. As we saw, it's simple LLM connected to a encoder. But the problem is that it uses full image patterns. It can use visual resamplers like QFormer, as do the other state-of-the-art models. And this can make training a bit slower than it has to be. And the reason the authors give for their choice is the production of instability in training when using visual resamplers, QFormer. It is also very data and compute efficient. As we saw earlier, it only uses 1.2 million training samples, or of magnitude fewer than other state-of-the-art models. So completes training in a single day, approximately 24 hours. But it's still unable to process multiple images. You can only feed in one image at a time. And the authors explain that by two factors. The first one is the lack of appropriate visual answering data sets that contain multiple images and reasoning across multiple images. And the second factor is the context window size, which is limited. The model achieves state-of-the-art results on most benchmarks, 11 out of 12 this paper, but it's still lacking when it comes to problem-solving skills in some domains. And as you might expect, just like other models, it can still hallucinate, and it can still produce misinformation care. One thing I would like to add is the simple architecture claim has gotten a little outdated since the paper came out, because Adept has published a much simpler model, a much simpler LMM called Foo, is simply a transformer, a vanilla transformer that use vision encoders, and it's also very performant and achieved very good results while being even simpler than LLaVA. That's it. Thank you for watching. Thank you for attending. If you have any questions, I'll be happy to answer.